We are here live. The only special guest, other than the normal ones, is our friend Michael Housh. So thanks for joining us, Michael. Bert was supposed to be here, but he bailed at the last second. And his excuse is that he has like little kids and stuff. I don't know. Seems lame to me. But today we're talking about admittedly one of my favorite topics. And the reason why it's one of my favorite topics is because it's kind of like setting the transformer tap properly when you're on, moving it when you're on 208 volts. It's like one of the things that nobody thinks about, or they don't think about it as often as they should. So we run into a lot of cases where systems can actually have problems because people don't follow the long line set guidelines from the manufacturer. But this is going to be like an ultimate discussion of RTFM. And of course, by that, I mean, read the fantastic manual, nothing untoward there. But this is really what we're going to do. We're going to go through some manuals. There's 3 different brands represented in the manuals that I'm going through. You have Carrier. What happened? Is somebody getting arrested? Is that you? Is that you, Matt?
No. It's me.
So
yeah,
they're coming
from the fire station.
They're coming after you. So we're going to talk about the different reasons why long line set changes things in the system, and because there are a couple different reasons, and then some of the common things that you see in manuals. But ultimately, you do need, in order to know specifically where the line is drawn with your manufacturer, you need to look at the manual. And it's in different manuals of different manufacturers. So sorry, they're not always the same. Some it's in the product data, some it's in the installation instructions, so on and so forth. The stuff we're going to cover today. But we will rock on and do this thing. All right, so I'm going to start by, I'm just kind of talking about additional charge. I'm going to start with you, Michael. So like when you guys do installs, do you typically measure line sets and weigh in charge as part of your typical install procedure? What's your typical practice there?
No, generally not, unless it's like mini splits or something like that. Typically, we would, most of my residential units, things are under 50 foot. 25 to 30 foot. So it's not something I have to generally take super precaution about, and we'll just open it up and then charge from there based on subcooling and stuff. It's really just, I know the proper way would be to read the manual and, put in whatever, but that's just not super realistic in my mind. Like I don't know.
Yeah, no, fair enough. How about you, Matt? Do you find yourself weighing in charge based on line length?
Yeah, so it's kind of similar to what Michael said. If it's like brand specific and they've really asked you to do it, which is mostly going to be like variable speed stuff, then that's when I weigh it in.
Yeah. And honestly, that's pretty common. It does come in handy when you do have significantly longer line sets, like you mentioned, critically charged systems. Things like if you have a microchannel coil in place where it does get a little bit more tweaky, that's where it can matter a little bit more. But kind of your standard for 3/8 liquid line is 0.6 pounds or 0.6 ounces, not pounds. Boy, that would be a bad thing. 0.6 ounces per additional foot of liquid line beyond whatever the manufacturer specs. Most manufacturers, like we talked about, 15 feet. And both Michael and I feel like we've seen equipment out there that's 25. But whatever the manufacturer's factory charge is, you look at whatever the additional line size is or line length is, and you can do it this way. And the easiest way, this is actually the one that's pulled from our site, hvacrschool.com. And we also have another one in the app that also takes into account variations in suction line size. And it gives you 3 different ways of displaying the weight in case you have a preference. If you like it all in ounces, if you like pounds and ounces, or if you like it as fractional pounds, we offer all the different things. But I put this here because one of the main reasons why long line length applications matter is because of the amount of refrigerant in the system. So rather than me talking a little bit, I want to turn it over to Adam. Have you used but before we talk about this, let me just finish that thought. So amount of refrigerant in the system really matters because the more refrigerant you have in the system, the more likely you're going to have compressor flooding or slugging. And that's mostly when it starts. So if refrigerant is allowed to migrate and condense in the compressor crankcase during the off cycle, or if there's any liquid refrigerant present in the evaporator coil or suction line, both of those things are really what we're trying to prevent. And so most of the accessories and the things that we add into a system when it has long line is actually just dealing with the fact that you have more refrigerant, and so it's more likely that you're going to have a flooded or slugging start condition, which is a really bad thing. No bueno for, we always think about setting our superheat. We want to make sure we have a proper superheat so we don't actually have an operational flooding condition with liquid coming down the suction line. But it's actually much more likely, much more often, that flooded condition happens because during the off cycle, refrigerant is allowed to condense in the compressor.
Another thing that this is nice for is if you're ever just like not really sure, like you just keep adding refrigerant to a unit and you're like, man, this seems kind of weird, if you to just go to the calculator like this and put it in and just kind of have an idea of, where you could reasonably expect to land when you're adding charge to a unit.
Yeah.
So that's nice.
Yeah, one thing I wanted to just pop up here, Gary said Bosch and EcoVert heat pumps are both 25%, 25-foot pre-charge. So thanks, Gary. You validated what Michael and I both remember having observed. So now I wanted to ask you this question, Adam. So have you ever had to reference one of these D-rate charts for suction line for making like maybe you go to an old application where changing a line set would be really hard, and you look at maybe changing the suction line won't be necessary possibly?
I have, but not specifically a chart like this. But yeah, I was kind of looking at like I'm trying to remember the manufacturer it was, but because I'm kind of like Michael, where I don't run it. Most of our residential stuff is fairly short. At times we run into where there's like condos on the third floor or something else like that, where there's no way you could possibly replace the line set. So yeah, one thing I found that is tricky in a lot of our like older R22 systems, you run into smaller liquid lines. I know this is kind of referencing the suction line.
Yeah.
And then once again, the larger units are the older R22s are usually 1 1/8 if it was done, the way it should, like a 5-ton or whatnot. But and that's one of the things that I do run into is when you have a 5-ton unit and then you actually look at the proper sizing, and then you're like, oh, I need a 4-ton or a 3.5 ton, and then you try to match it up. Like, what's going to happen? Is 1 1/8 okay? And I think that the whole velocity thing and oil return is something you need to be concerned about.
Yeah, this actually comes, this chart that we're looking at right now comes from a Goodman long line guideline. Usually you'll find this, I think, in product data is the place that you would generally find it, sometimes installation instructions. But most manufacturers have something like this. This came up recently for us. We're doing a really big apartment job that Roman talks about a lot. And initially we were going to run like, I don't know, 1 1/8, 7/8, some really large size. And then when we looked at the D rate, it was like next to nothing to go down to 3/4 inch based on the lengths of most of them that we were running. And in fact, you actually get an advantage in many cases where your evaporators are lower than your condensers, which is more common in most cases. Condensers on the roof, there's actually an oil return advantage there too. So you really don't want to go larger than you need to in a lot of cases as well for oil return purposes, kind of like we talked about a couple weeks ago. So that's another thing. But this isn't specifically long line related as much as it is like, just realize this is another reason why line length matters. Almost all equipment has a maximum line length that you can't go over in any circumstance. But in many cases, the line length is going to be a big factor in what size you do select. And you can see this isn't talking about oil return. This is talking specifically about capacity. So even though, let's say you have a 200-foot length, it's not talking about condenser higher, evaporator lower, or it's not covering any of that. It's just saying, hey, this is what you lose in capacity. Because you're getting a pressure drop across your suction line. And that's not a good thing. We've talked about that before. Pressure drop across suction line is not great. Some manufacturers will also talk about things like going to 1/2 inch suction insulation versus 3/8 when you get to certain line lengths for the same reason, where you get more temperature gain on your suction line. So it varies manufacturer to manufacturer. But so just keep this in mind.
it's a compression ratio and like a mass
Yeah,
flow rate kind of a thing?
that's
Is
what
that-
this
but-
that's what this multiplier is doing, right? So what happens when you have, let's say, if you look at the top one, let's say you have a 100-foot suction line and it's half inch on this 18,000 BTU system, ton and a half system. What that means is you're dropping down, you're losing 6% of your capacity, and you're losing it because of compression ratio. It stands to reason, right? Like that's what's happening is you have more pressure drop across your suction line. Advantage is you have better velocity across your suction line, so your oil carry is actually going to be better. You're going to move oil better in that case, but your compression, you're losing that capacity because of compression ratio, which means that your compressor is also going to run a little hotter too. Now, again, they're telling you it's allowable because otherwise it wouldn't even be on this chart, right? Unless elsewhere it tells you that it's not allowable. So these are all things to consider.
I think this would be kind of cool. Like I know with that the apartment job that you're talking about, you guys are probably looking at, when you have many different line sets and you're stepping it down from 1 1/8 to 3/4, there's a fairly substantial amount of savings there.
Right.
But you could also look at this like in a design aspect, like, and look at what your load is and what your BTU, your capacity of your equipment is. If it's slightly oversized, hey, I could use a smaller line set and actually be a little bit closer to a match size machine then.
Yeah, I mean, you're still losing that. That's not the best way of doing it.
It's not, but if it means like, it's more labor to install larger line sets, it is more materials, it's more difficult. Everything, I mean, there's more benefits if you can do it, I would say.
Yeah, right.
Would be my preference for sure.
Right, and that's exactly what you're saying is exactly true. If you are going to go down in suction size and it's a little bit longer of a line set, especially, you need to look at your loads and say, do I have this buffer? And if I do have this buffer, there actually may be some advantage in terms of like dehumidification, like where you will actually dehumidify better because you'll get a little bit longer run times, a little better load matching. So it's something to definitely, absolutely consider.
So you would never want to go up in size though, right? That would cause, I mean, if you're just thinking about suction line sizing, you wouldn't want to go up because you're going to have oil return velocity issues, things like that.
Well, you can't go up from what the chart allows, right? Like, okay. So, but you can see it's pretty, it's pretty hefty. Like here it shows you 1.5 inches or 1.125 inches on a 3.5 ton system. And again, that's where you get to certain cases, and this is what we're going to talk about as we move forward. Then the application matters, right? Is the condenser above the air handler? Is the condenser below the air handler? Or is the condenser level with the air handler? That's where it really starts to become more of a consideration.
I'm kind of, I know we were, on a couple of weeks ago, the whole conversation on traps and that, but like, so why is it certain manufacturers would recommend a trap in certain situations and others might not?
So it really depends on, so there's a couple of factors. It depends on what they're doing velocity calculations, right? And they're looking at their own particular testing, whether it's a heat pump or straight cool matters. Obviously it depends on what the oil is. So if you run into cases where somebody's using PVE versus POE, that's going to change it. The refrigerant is going to matter. But obviously if it's 410A with POE and you have exactly the same mass flow rates, in theory, they should be the same. But manufacturers aren't, it's not like they're running through a central, clearinghouse for what they approve or don't approve as well. So it's based on their own individual testing of oil return. I mean, you will see there's like almost all manufacturers have the same sorts of data, but there is pretty significant variations between what they recommend and what they don't. Like Goodman, I think it is, starts recommending an accumulator be installed outside of the condenser, like pretty quick in their long line applications. And almost nobody else does that. Maybe it isn't Goodman, but I'm thinking it is. And like, that's a pretty draconian move. And the reason why they do it is because up until recent and still maybe even now, they were using more fixed orifice metering devices when other people were using TXVs. And so when you're using fixed orifice, it's more likely that you're going to have flooding. And so when you have more refrigerant in the system, it also increases those odds. So it's just different ways of skinning a cat there. And I don't know why you'd want to do that. Why would you want to skin a cat? I'm not sure. It's a good question. All right. So this next thing that I want to talk about is fitting losses and equivalent feet. And this actually relates to the chart that we just showed, right? So this is sort of like in duct. This is actually showing a friction rate, a suction line friction rate equivalent feet chart. This is not related to how much refrigerant you add. And that's a distinction I want to make. So it's not like you're using this and being like, oh, okay, well, this counts as, 12 more feet because I have a liquid line solenoid. So I have to add in, 12 times 0.6 ounces more refrigerant. No, that's not the case, right? That's all about just filling your liquid line. This is about equivalent length for that derating chart that we just looked at. And because it does matter. If you have a solenoid in place, that's a significant pressure drop. Same thing with a suction filter dryer. That sort of thing. So anything to add there? I told you I was worried this was going to be a monologue. So here we go. That was kind of a boring one.
Yeah.
All right. So I'm going to ask this question. Matt, have you ever seen different size liquid lines other than 3/8? Like, do you run into that much in your market?
Yeah. I saw one today. It was a
5/16
whatever smaller
than
right?
5/16. That would be
I think it was 5/16 or 1/4 inch.
Yeah.
And I was curious, right? I thought, would that derate the equipment? Like if it's got a smaller, there's less refrigerant in that line set. That was I've always been curious about that.
Yeah. So the way that it potentially can derate is once again pressure drop. So if you have a smaller liquid line, pressure drop can cause flashing, and that depends on the length that it is.
Yeah. Can you talk us through that? How that would happen?
Let me see. I want to check and see what charts I have here. Actually, I don't. Yeah, I don't have any other chart. I didn't remember what I put in here. Okay, so imagine that you have a evaporator, an air handler that's higher than the condenser, and it's a significant length, right? Most manufacturers are either going to tell you, they're going to give it. There's another chart that's going to talk about this specifically. What size liquid lines you can use in different situations, what length you can allow. And Carrier has one that's really interesting because it will talk about, all right, what happens if they're the same level? What happens if the evaporator coil is higher? What happens if the evaporator coil is lower? And what you'll notice is if the evaporator coil is lower, you actually can use a 1/4 inch liquid line more the greater the distance differential. Okay, so I'm going to say that again. The greater the distance differential between a condenser that's higher than an evaporator, the more likely you can use a 1/4 inch liquid line on a straight cool system. And the reason is because you actually get static regain. You don't get pressure drop, you get pressure gain. It's just exactly like having a water pressure, right? If you have the pressure at the top of a column of water and the pressure at the bottom of a column of water, where's the pressure higher? At the bottom of the column of water, right? Even if it's flowing, you get static regain in that. And so that's what happens. You actually get higher pressure at the bottom, so you don't get pressure drop, you get pressure gain. So going to a 1/4 inch liquid line is actually advantageous. And if you look at this chart here, it covers that. Like it basically says 1/4 inch plus TXV, no accessories needed within allowable length. So as long as your outdoor is above your indoor, if they're on the same level or outdoor below indoor, indoor. Yeah, you don't need anything additional. Now, what's interesting is here it says outdoor above indoor that you do have a maximum length allowed, and that may even be because of the maximum limits of the additional pressure that you're gaining. That's one I didn't notice on this chart before. But regardless, like if you can go down in liquid line size, it's not just an advantage because you can use cheaper copper. It's also an advantage because you have less refrigerant in the system now. And that solves a lot of these problems that we get. Because again, most of the things we're using accessories for is because we have so much extra refrigerant in the system. I'll give a story. I worked on a house where the liquid line was like excessively large. It was like a 5/8, or I think it was a 5/8 liquid line. And it was just that way. And we couldn't run another one any reasonable way. It was like encapsulated in concrete. There was like a garage in the way. It was going to be this whole big deal. And I didn't even show up until we were halfway through it. And the guy just kept adding charge. He's like, man, this thing is holding a lot of refrigerant. And it wasn't that long of a line set, but we still ended up having to do these long line set kind of changes to the system in order to prevent issues that you would get. Now, again, that was kind of off the manufacturer's data, but it doesn't hurt to have too large of a liquid line. Other than that, now you have way too much refrigerant in the system and the cost of the copper. And so as long as you accommodate for that, then you're okay. And that's why we use 3/8 liquid lines across all. I mean, have you ever wondered that? Like, why do we use the 3/8 liquid line for a 1.5 ton and a 5 ton? Like, those are pretty significantly different capacity systems. And the reason that you can is because the 3/8 liquid line is actually very oversized for a 1.5 ton system. But it's because those systems have pretty small charges as it is. It's not a big deal. It doesn't hurt to have too large of a liquid line because you don't have issues with oil carry. Velocity is not a problem. And so having low pressure drop on across the liquid line is not a bad thing.
So it's sort of like when you're talking about like pressure loss, it's almost like it's similar to ductwork, right? Like where like the refrigerant flowing through the copper, there's resistance there, so you're losing pressure essentially, right? As that refrigerant. Okay, yeah, interesting.
Yeah, and that's a key thing, because then people will be like, okay, well, it's the same on the suction line too. No, for one reason, oil carry, right? We can't have too big of suction lines because we have to carry oil with it. And if you have too big of a suction line, your velocity drops and it stops carrying oil, right? On a liquid line, we want as little pressure drop as we can. The only downside is if you have too big of a liquid line, now you have more refrigerant than you need, which increases the odds of off-cycle migration and flooded starts, right? So that's the reason. So as long as you compensate for that, well, then you're fine. Now, the downside of also is that you don't want bigger copper than you need because that costs money, and you don't want more refrigerant than you need because that costs money. So there's these really these four things that we have. Copper costs money, refrigerant costs money. We don't want too much refrigerant because it can result in flooded starts and equipment damage, and we need to have proper velocity for the purposes of oil carry. Other than that, make your copper as big as you want, right? But yeah, that's still something we have to think about. Anything else you guys want to add here?
I was going to ask.
Out at you.
I've seen a couple of times that I've never really taken the time to dig into it, but when you have an evaporator below the condenser, right? And like I've had times where we replace an old system and you cut into the line set at the evaporator coil and oil just pours out. It's like you feel like it's like half the oil of the compressor. I was in my head, I'm thinking maybe that was an oversized line set, or maybe it was low on charge. Like, what would cause that?
Yeah, it's low velocity, right? So it could be oversized suction line. It could be a case where it was supposed to have a suction trap and one was never installed, right? That's another thing, especially if it was mineral oil, because there was a lot more cases where you were supposed to have suction trapping in old mineral oil cases, especially when the evaporator coil is lower. I mean, in grocery refrigeration, this is what we talked about. We still have that going on all the time. But the other thing is, so like what impacts velocity? You know, if we think this through, all right, the amount of refrigerant, clearly, right? The sizing of the suction line, obviously. What happens if the compressor is not pumping properly? Well, that impacts velocity, right? So it could be a compressor capacity issue, potentially. But one of the most common is actually your evaporator coil running colder than it's supposed to. And what's the number one reason your evaporator coil runs colder than it's supposed to?
Lack of airflow.
Lack of airflow, right? So low airflow, why does that cause? Because then this is actually something that somebody was wanting to argue about. They're like, well, yeah, but then it's more dense. Well, again, remember, it's a vapor, right? So it's not, we're not talking about a lot of density here. And what happens when you have lower suction pressure on the system? You have actual less pressure differential, right? So you do have less mass flow rate. We know this. I mean, you see your compressors get derated the lower your suction pressure drops. It's also a compression ratio thing. Your compressor, if you think of your compressor taking little gulps of suction gas every time it spins around, or every time that piston goes up and down, it's taking little gulps of suction gas. And if that suction gas is at a lower pressure, it's less dense. So it's taking smaller gulps. It's not moving as much velocity. So there's several different kind of compounding factors there. Besides the fact that also when you run and this isn't probably the main factor, but it is at least one, when you run a colder evaporator coil, you also have thicker oil viscosity too. So there's lots of reasons why it doesn't carry as well when you run low airflow. And if you start to pay attention on systems that you get a lot of oil in the suction line, it may be down at your ports. And like I said, there's cases where you cut a condenser out and it's like a bunch of oil pours out of your suction line, or it could be at your evaporator coil. If you pay attention, it's going to be a lot of cases where you had bad airflow to begin with. That's the most common one that I see. But it could, like I said, could be trapping, could be suction line size as well. Could be that they just
then
didn't
it's
follow.
oil from the last 3 compressors since
Right.
it had airflow and you just kept swapping compressors in.
Right. And honestly, I would watch for that, because when you get systems that have massive amounts of oil in it, that often is the case, right? Because and this is actually something I talk about, new compressors come with oil in them, a full oil charge. And so when you take that old compressor out, that's another reason that it's good to dump that oil out and just see. Like, it's good because you can test the oil for acid and that kind of thing as well. But it's good to dump it out and see how much oil is in this thing. Because if there's no oil in it, you got to figure out where the oil went. That's why that compressor failed. And it's a massive reason. I think it's actually much more common. People talk about flooding as being one of the main reasons compressors fail. But actually, when you start to cut compressors apart, lack of oil and overheating are actually just as common, if not more common. Oil breakdown because it ran too hot. And again, the different reasons, but we get sometimes super fixated on flooded starts or flooding as being the thing. But where did that oil go is a really good question.
I know that before they, I've been using the pipe wiper recently, and in the last handful of years, and like we'll run it through 2, 3, 4 times just to make sure, like, because you'll see more and more oil come out every time. And before we had that, I remember years ago, we would bring a nitrogen tank into the house and blow out, and somebody would have like a rag on the outside and just hold back pressure, and every so often, like, let go of it and just get bursts of oil out. We just do it if you're keeping the line set,
Yeah, when that's coming out of the suction line and it's a significant amount, that's an indication of the, because you shouldn't have significant amounts of oil in that suction line. Don Gillis posted here, and it's good to see Don in the chat here. He posted a couple things. First, he said mineral oil. Yeah, if you had mineral oil in it, that's another reason why, because mineral oil was more finicky. It didn't carry as well. And so you would have a lot more cases where you would have to do, like it said here, like he says here, a trap of the EVAP, an actual oil trap. And I think it's Lennox. One of them differentiates between an oil trap and a inverted trap. This is something that Matt and I talked about a couple weeks ago. I want to see if I had it here. I don't know if I do or not. Oh yeah, here we go. And this is a really good distinction, because here it shows, all right, outdoor unit is above the indoor unit. Oil trap at the indoor, yes. And so it gives an oil trap at the indoor unit is required if the elevation difference exceeds 80 feet. And that's, of course, within the proper sizing guide for this particular unit. So there's sort of a but there. You have to check these other things. But that oil trap is this small trap that is designed to help carry oil up that riser. That's not the same as an inverted trap. An inverted trap is when your air handler is higher than your condenser to keep from liquid refrigerant dumping down that suction line when the system comes on. Totally different purposes there. And you'll see, like, I didn't want to include basically entire manuals from the manufacturer here, but this manufacturer has separate ones: outdoor unit above indoor unit at the same level, and indoor unit above the outdoor unit. They're all different accessories that you would use.
Could we talk a little bit about a liquid line solenoid? Like what's happening when you need a liquid line solenoid? Like what is the purpose of that?
Well, the first thing is, do any of you guys worked on much refrigeration? Not really.
Not
Okay.
a
I worked on a wine cooler.
Yeah, I know.
Had
That's like the entry drug to refrigeration.
I was like,
You go
what
to
is
some
this
rich
thing?
person's house? Yeah.
Yeah.
Those are fun. So one thing you'll see a lot in refrigeration is a pump down solenoid, where a system actually pumps down and then shuts off on suction pressure. I actually worked on an air conditioner in a grocery store that was set up that way just because they never ran a control wire from the condenser to the controls. And so that's literally how they were controlling on and off of the condenser. And a pump down solenoid is where it's literally pumping down, and it's not pumping down to zero or anything. It's just pumping down to get all the liquid out of the evaporator coil and and basically everything, just putting in all the condenser essentially. That's not what this is. So this liquid line solenoid, all it is, and this is what's so annoying and kind of dumb about it, all it is it's just creating a barrier. It's just shutting off, so that way refrigerant can't make it into the evaporator coil and the suction line, right? And the off cycle. So when the thing shuts off, you don't want a bunch of liquid making it into the evaporator and suction line so that when the compressor goes on, it pulls it all into the compressor. That's all it is. But if you have a hard shut off TXV or a non-bleed TXV, that really performs the same function. So like, and that's why a lot of them are like, they only require it on a heat pump. You'll see this for several manufacturers. It's only required for a heat pump. Well, why is it only required for a heat pump? Well, it's because in cooling mode, it has a TXV, and the only time it has a piston, the only piston located in the system is the heat mode piston. And so that's the only time you run the risk of having oil migration. So it's kind of silly to me because there's such a pain in the butt to install. I just think to myself, why don't you just install a TXV then? If like it seems like a goofy workaround. But that's literally all it's doing. It's just when the system goes off, it just creates a block so it can't, so that refrigerant can't migrate into the evaporator coil and suction line.
Cool.
Make sense?
Yeah.
And are there, I may be wrong, but like, don't they have like a decent pressure drop though? Like, so sometimes if you have a 3/8 liquid line or whatever, you can't necessarily just put a 3/8 solenoid valve on.
Yeah, you have to pay attention to that. I mean, that's why if you go back to this kind of shows you the difference. It shows here that there's an equivalent length of 12 feet of a liquid line, a pressure drop associated with a liquid line solenoid. That's what this manufacturer is showing. It's significant. In order for that valve to activate, it has to have a pressure drop across it. So it's sort of it's another kind of annoying thing about them. It's unrestricted in one direction and only restricted in one direction. But like it shows here, like I was just saying, if you look back at this chart, it's like if it's a heat pump, it needs it. If it's a heat pump, then it needs the liquid line solenoid, and if it's straight cool, it doesn't need it. Well, why is that? Well, it's because they both have a TXV indoors. Either way, it's just that on a heat pump, you have a fixed metering device and heat mode. So you're literally only installing it just to protect in heat mode, and it's like it's just annoying because like if you would have put a TXV in. Then you wouldn't have even needed it. And it's such an excessive, like you mentioned, additional pressure drop that you're putting into the circuit. Let's see, what else do we have here? Crankcase heaters, another really huge misconception. A lot of times people think that you only need crankcase heaters in cold climates and that it's to keep the compressor warm. So I'll ask it as a question. Adam, have you ever on a system installed a crankcase heater and like an aftermarket accessory crankcase heater on a piece of equipment?
No, never. I have noticed, I mean, not kind of off topic, but I have noticed that on, if you actually read the manual, certain pieces of equipment will say they want power to the outdoor unit for X period of time before you start it up.
Yeah. Yeah. And again, because a lot of people will see this and they'll be like, well, why do you need all of these things? Right? Like it does seem a little excessive. Like crankcase heater, because look at it. I mean, look at your right column here. If this is a heat pump and your line line length exceeds 80 feet for single stage, and actually, I think it's probably in a different chart. This isn't different, but generally speaking, it's 80 feet or more is kind of your standard long line application. You've got to do all of this stuff. So crankcase heater, hard start kit, TXV indoors, liquid line solenoid at the outdoors. You don't have to do an inverted trap because the outdoor unit's higher than the indoor unit if you flipped it, and you need to have an oil trap. That's a lot of extra stuff that you have to do because they all serve different purposes. So go through it. Crankcase heater, what does it do? Crankcase heater keeps liquid refrigerant from condensing in the compressor itself, right? So none of the other things do that. They prevent it from being in the evaporator coil and the suction line, but the only thing that prevents liquid refrigerant from condensing in the compressor itself so that you don't have a flooded start is the crankcase heater. There is nothing else that does that. there's different types of crankcase heaters. Some manufacturers use like trickle through the windings on the compressor. There's different techniques. Some use a belly band, the old train insertion ones. I don't know. Did any of you guys ever work on those where they would like always break off right at the base and then short off on the bottom of the condenser? That was one of my favorite service calls, because that was back when I didn't believe that crankcase heaters did anything. So I would always just cut them off and just be like, yeah, ma'am, it's a free service call. I was really bad. I would give people things for free all the time. So not only did I make your system work worse, but I also gave it to you for free. So you can't complain.
You got it back on.
But at least your breaker's not tripping now, right? So it'll trip soon when your compressor fails from flooded start. But anyway, those big orange train compressors, those things could eat liquid like crazy anyway, because they had all that extra space in there, basically had an accumulator built into the thing. Anyway, that was a stupid side note, but you do need them in these cases, because when you have additional refrigerant, again, it goes back to what's the difference in a long line? You got more refrigerant. When you got more refrigerant, it increases the odds that you're going to have refrigerant condensing in the compressor crankcase. And to your point, Adam, the reason why they tell you to do that when you first turn it on, let it, leave it powered for a certain amount of time, is because there's a really good chance that there's going to be liquid in that compressor crankcase. It literally was just sitting there with liquid full in that condenser. What really is to prevent some from being in that compressor crankcase. And so they want you to kind of drive it out with running the crankcase heater first. Now, it's completely unrealistic.
It's like 24 hours, right?
Right. I don't know of anybody who's ever done that, but there is a reason for it, and it is a good reason. So instead, what you do is just take a torch to that sucker for 10 minutes. Just get a big old blast creek, just get it nice cherry red on the side before you fire it up. Somebody's going to actually do that now and sue me. That was a joke, people. So that's the purpose of your crankcase heater. Hard start assist. It's the same. Hard start kits. And again, this varies from manufacturer to manufacturer. But a lot of times people will say, well, if it's a scroll compressor, you don't need a hard start kit. But if you look at the long line data, a lot of manufacturers, when you have long line sets, will still recommend a hard start kit on a scroll compressor. Now, I question it a little bit, because again, you're not working against that column like you are in a reciprocating compressor. And sometimes I think they just leave it in there because they're just too lazy to take it out of their specs and like specify it for different compressor types. But you will see it a lot. And again, it's just because now that you have a hard shutoff TXV, you're not bleeding. You are working against a higher pressure differential when the compressor starts. That's really all it is.
I feel like there's some manufacturers that even just if you have a hard shutoff TXV require a hard start assist, even though they don't come with it, but their coil comes with the hard shutoff TXV.
Right. It's kind of silly. And what I see is it's usually not an issue, because again, and this is one that kind of frustrating. Like almost all the single phase equipment that comes out of the box is rated for 208 as well. Like, and if you think about this, you're getting significantly less energy to the compressor in a 208 application, 3-phase 208, than you are in single phase. And so what I see is that it really generally isn't a problem unless you have a long line set and you have a hard shutoff TXV and you have 208 volts or some other reason for voltage drop. And so that's where we see it a lot, is in commercial buildings, like self-storage, where you've got really long line sets and they've got 208 power. That's where the hard start kits come in. But again, the manufacturer's not like, they're also trying to not make their specs too complicated. So when you have a system that comes out of the box that's rated, it's supposed to be able to run all the way down to, 198 volts or whatever it is. They have to design it so that way it's not going to be a problem all the way down to that voltage. And if you imagine long line set, hard shutoff TXV, and 198 volts, well, yeah, then that would be really hard for it to start and would definitely require a hard start kit. Again, I'm talking out my rear end right now, because most manufacturers, if they heard me saying this, would be like, no, you just do what we say and don't question it. Just do it, but we just know realistically.
Our docs are perfect.
Right. Just do what we say all the time. But we just know realistically, like there's a lot of equipment out there that doesn't have hard start kits that technically, based on the information, should have it. And like to your point, Michael, a lot of it isn't even on the long line spec. It's just like, if you have a hard shutoff TXV, you need to have a hard start, and they come with a hard shutoff TXV in their unit. So it's like, well, why didn't it come with a hard start then? So it's sort of like, to me, that's where it kind of shows that they kind of know it's not actually necessary in all cases. And you guys know my stance on hard starts is I don't love them if you don't need them, because it's just another thing to fail. And if your potential relay fails, that can be a real issue for your compressor. Or if your run capacitor fails, that can be a real issue for your compressor if you still have a functional hard start. So even in a perfect world with a factory hard start, it still can cause problems if you have other issues. And that's my only beef. Besides the fact just adding in additional stuff for no reason is not my favorite. But again, listen to the manufacturers. I like Don Gillis is laughing at me at this point, which I definitely deserve.
Yeah. Did we cover oil trap on the indoor? I know we kind of, that's like where the suction line has to come kind of over the top of the coil, essentially.
Well, that's inverted trap. Okay, so inverted trap is when you come out of the evaporator coil, you go up, and it's a pretty good amount too. And you have to look at the specs, but you go up and over and down, right? That's inverted. It's like, again, just think of a normal drain trap, right? Normal drain trap, P trap goes down and then back up again, right? That's an oil trap. That's how an oil trap works. It goes down and then back up again, and it's down at the bottom, right? So oil collects in it. And again, like we talked about in the commercial refrigeration live stream that we did, you want the oil to all drain into that trap, and then it creates a seal, and that forces that oil up that riser. That's what that's for. And like here, it's showing it, because in this case, it's showing the indoor unit is lower than the outdoor unit. So it's going to collect right there, and we got to get it up there. And again, that's not universal. It depends on the distance of differential. It depends on the manufacturer's information. And really, it also depends on the suction line size. Again, this is another generalization that they're giving, where it says, like, if an elevation distance exceeds 80 feet, well, it's like 80 feet with what suction line size, right? So they're kind of trying to generalize.
Yeah, it's covering their bases.
They're covering their bases, right? Whereas if you're in an engineer job, like we see in market refrigeration, that engineer is going to tell you, here's the size suction line, here's the size riser, and it's usually going to be down a size. Here's the size trap that you're going to use to get that oil carry up for that exact distance, for that exact refrigerant velocity that we're running, based on that evaporator temperature, based on the refrigerant, based on the oil type. Those are all the mitigating factors. So again, oil trap is different than inverted trap. Inverted trap is preventing liquid refrigerant from dumping down the suction line. Oil trap is to help carry oil up the riser. Two completely different purposes. And again, we're only looking at one of the three options for this particular. We're looking at one manufacturer and one of the three charts for that manufacturer, which is outdoor unit above the indoor unit for this particular thing. And then liquid line solenoid, which we've already talked about, and again, TXV, the advantage again for the TXV is that hard shutoff function, where when the system shuts off. And again, this is another one that I think is important for people to know. Actually, I'll ask this to you, Matt. I'll do a Jim Bergman on you, what he always did to me, just put you on the spot. So why is a hard shutoff TXV hard shutoff? What makes it hard shutoff? What magic happens that causes it to shut?
The compressor turns off.
It does. That is true. But why does the compressor turning off?
I know. I you know what is funny is I've probably heard you talk about this like 3 or 4 times, and
there's so many different ways you can explain it. Okay.
Yeah, it's like
so here's the easiest way. Here's the easiest way to explain it, which is that what is the superheat of your system when the system is off?
0.
It's 0 superheat, right? What does a TXV do when you have 0 superheat?
It closes.
It closes, right? That's its job, is to maintain superheat. And so it closes. That's the easiest way I can think of explaining it. And that, because that is actually true. It's just like, it's easier to explain it that way than to say, well, what happens when the system goes off? Your suction pressure increases, and your suction pressure increasing is the closing force of the valve and the external equalizer, which then drives the valve closed. But you see the same effect happen whenever you nitrogen pressurize a system with a hard shutoff TXV. If you're like me and you put nitrogen in the liquid line and you watch it go up on the suction, that's what I always do. So I pressurize the liquid side and I watch it go up. And I learned to do that because back in the day I worked for this big company, and they would always have sand on the line sets because the installers would push line sets without caps on them and get sand full of them. So I always wanted to see if I had a restriction right off the bat. And so I would just watch to see, all right, if I put pressure and the liquid line, does the suction come up? But when hard shut-off TXV started becoming standard, I would watch it go up in the suction, and all of a sudden it would stop. And then my head pressure would keep going up. And I'd be like, what the heck is going on here? You know, like there's a restriction that all of a sudden just occurred. And what it is that my external equalizer pressure finally exceeded my bulb pressure, right? So it forced that valve close. But again, another way of saying that is as soon as it hits zero superheat or low enough superheat, that valve shuts off. And that's what happens when the system is off. You run zero superheat. I like Neil's, talking refrigeration, Brian's happy place. There's a couple. Capacitors is one. And yeah, this is another one.
When you have a bleed TXV, is the only difference a bleed TXV doesn't shut all the way, and it just has like a little. Yeah,
it has a bleed port. Like so that's the funny thing is people say, oh, a hard shut off TXV, that's some sort of fancy TXV. It's really just a TXV. Like that's just how they work. And so long as they can go all the way shut, it's hard shut off. But either they can have a bleed port, or in some of the older ones, they just weren't really made that well. So it's like you just got more bypass through it. Whereas now modern valves, when they're shut, they're shut. And again, even then, like you will often get a little bit of bleed through. But they're surprisingly tight though. Like I said, if you do that nitrogen test, you'll see that they slam pretty darn shut. All right. Anything else we can think of here? No? Any questions from the audience? I haven't been paying any attention. And we have any good questions? Let's see here. Here's one. Al Anonymous said, I've installed crankcase heaters on systems that did not come with one, nor required one, and it stopped destroying compressors. Yeah, I have too. In fact, one of the things that I've consistently done whenever I have anytime a system takes out more than one compressor. So we had one, we didn't even install the equipment, but we came to the system and replaced the compressor. And then within like 6 months, it took out another compressor. That's what I had us do, is go through and basically do everything here, other than the hard start kit, to just try to resolve the issue. And do a go ahead and flush everything with the pipe wiper and get any existing old oil out, and try to clear everything. I think we even pulled the evap out and just like flushed it with solvent, trying to make sure that there's everything out of it as much as we could get out. But yeah, it's much better at that, because at that point you own it, right? If it happens again, the client's going to be really upset. So just go ahead and do everything that you can do. And again, all of this is on like a gradient scale. The idea that you don't need one just means that the odds are less that it's going to take the compressor out, right? But you still could get liquid condensing in the compressor. But looking at things like, is the system overcharged? What is your evaporator airflow? Than anything else. And I'm not a fan of like, adding in a bunch of acid inhibitors and all that stuff, because often I think that causes more problems than it solves. So that's a tool.
One compressor, shame on you. Two compressors, shame on me.
3 compressors, shame on all of us. just shame to share all over the place. Here's one. Corey Peters said, does using a single pole contactor really provide warmth to the compressor by giving it one leg of power 24/7? Does anyone want this one? Ready?
We don't know, Brian. Or maybe
ready.
Yes.
The answer is yes. Just yes. It doesn't do it automatically, right? It's not like it just does it. It depends on how it's wired, right? It depends on how it's designed. So just because you break one leg, that it's not still energized, right? Just because if you break one leg, it's like, that would be like saying, like anytime you broke one leg, that still it was energized and it was still getting hot for any electrical device. And that's not true. If you break one leg, there's no path. It's not doing anything, right?
Yeah.
But that's where you have that design with the single pole contactor, where you actually connect one leg to the underside of the switch. And so now it's actually bleeding of the crankcase heater. Sorry, to be clear. So now it's actually bleeding. It's using the crankcase heater and one of the windings to feed back through. And it's designed that way though, right? Like it's not like you're just using the compressor winding and just by having one leg energized, it's going to do that all the time. Now there is a wiring configuration where it actually only uses the compressor windings. and it uses, if you've ever seen that weird split capacitor design, I mean, this is kind of old. This is like an old GE thing where you would have 2 run capacitors. It would have a big one and a small one, and it would actually, you'd wire that smaller run capacitor separately, and that smaller run capacitor would basically act as a current throttler through one leg of the compressor, and that compressor leg would then be what heated the compressor. But that's all by design, right? You don't just put in a single pole contactor and that magically acts as a crankcase heater. That's going to do absolutely nothing. But on the other hand, if you replace a single pole contactor, which I think this is the question, if you replace a single pole contactor that is designed in this way, and you just replace it with a 2-pole and wire it exactly the same, it's not going to have a crankcase heater anymore. So you have to actually change how it's wired at that point in order to accomplish it. And even then, it's not going to function exactly the same as it did before, because you're going to have now more current through your crankcase heater than it's really designed for. So there's some tricky stuff here, which is why the right way of doing that is either go back in with a single pole when it's that type of system, or go ahead and shunt one of the poles. So just take a big piece of wire and just go around and basically turn it into a single pole. Mm-hmm. Good question. And really, if Carrier does that or did it for a long time, I don't know that anybody else does that. It's not a universal thing. Anything else you guys can think of? Because I'm fine with ending early. You know, we've always said that if we need to end early, we will. And I did just monologue, like I said, I wasn't going to.
Yeah, no, I thought that was great. I mean, I learned a lot.
Yeah, me too, for sure.
Yeah.
I'm happy.
Which begs the question, why was it a live stream? It could have just been a regular video. It could have just been a video of me talking, but that's fine.
So what I got out of tonight is never run an 1.1/8 line set.
Ever again, right?
Ever.
Never, never, right? Even if it's let's look at this one here. Even if it's a 5-ton. Well, actually, it is kind of a good point here, because even all the way on this particular unit. So again, to be clear, this is only one unit, but on this unit, 5 tons, even at 250 feet, you're losing 5% of your capacity at a 7/8 suction line. So in a lot of cases, you can actually get away with going to 7/8 rather than 1.1/8. But again, you're still losing it. It's still a cost. 5% isn't nothing. So,
and I don't even think.
But if you put a 5-ton in, it's oversized. So,
right. Back to Jenry Garcia's stance on that. Yeah.
I mean, I haven't seen new units call for 1.1/8 ever.
Well, no, people put them in because some of them will come with an 1.1/8. Brain fart on whatever the connection is at the compressor.
Right.
Yeah, it seems like it was something that was more, in the past.
Yeah. I did get a comment about my glitchy camera. I do need to get a new camera. Yes, I know I look like an AI because it keeps glitching. I get it. I'm not part of the Matrix, or am I? Cool.
You're the embodiment of air conditioning come to life on the internet.
Right. Yeah. Yeah, absolutely. All right. Well, hey guys, thanks for taking the time. Everybody who joined us, appreciate it. And we'll catch you on the next one.